A very good morning to all of you. And to begin with, I'd like to thank the organizers for giving me this opportunity to come here, attend this conference, and speak to you guys. So it's been just about exactly 1 year since I arrived in Cambridge to do my postdoc at MRC LLB. So I don't have enough to talk about my postdoc work because it's in the very initial phase. What I would like to do is to tell you what I did in my PhD when I was in India. So, our lab has been studying, proofreading mechanisms which are involved in correcting errors during protein biosynthesis. And I was involved in studying a very specific type of proofreading, which we named chiral proofreading. So to begin with, I'd like to tell you that proofreading is important not only in our day-to-day life, but also in biology. And I hope that I'll be able to convince you about this fact by the end of my talk. So to give an analogy, I would just like to show you this cartoon. So in this cartoon, if you see, there's this guy who is about to send a message to a girl, but he has not proofread it, and he's probably in for a bit of trouble. So the bottom line here is never underestimate the importance of proofreading. So now coming to my research. So basically, I think all of you must know this, that the flow of genetic information from DNA to RNA to proteins is very tightly regulated, because each of these steps are associated with errors, and therefore each of these steps require proofreading. So my PhD work involved studying the aspects of proofreading in the first step of protein biosynthesis, where an amino acid is attached to the tRNA for it to be taken to the ribosome. So there are two kinds of errors which can happen during this coupling step of amino acid to the tRNA. For instance, a very similar L amino acid can be mischarged on a tRNA. For instance, L-serine can often be mischarged on tRNA threonine by threonyl tRNA synthetase. So this is one kind of error that happens during this coupling. The other kind of coupling happens that a D amino acid can be mischarged on a tRNA. For instance, D-tyrosine gets discharged on tRNA at a very high rate by tyrosine tRNA synthetase. And just to inform you, the presence of D amino acids are now known everywhere. It's ubiquitous, and some of these D amino acids have very important physiological functions. For instance, D-serine and D-aspartate, they are important mammalian neurotransmitters. So D-serine is ubiquitously present everywhere. So I studied specifically the error that happens of this kind of mischarging and the way it is rectified in the cell. So once a D amino acid is mischarged on a tRNA, so these D amino acid tRNAs can either deplete the free tRNA pool for L amino acids, thereby causing toxicity, or it can actually lead to the misincorporation of D amino acids into the polypeptides, leading to global misfolding and hence cellular toxicity. So in any case, this entity needs to be eliminated from the cell. So there's the enzyme which is called D amino acid tRNA deacylase, or in short DTD, which does this function, and it goes and specifically looks for these D amino acids discharged on tRNAs and cleaves them off. So we were interested in understanding the mechanism of chiral discrimination or enantiomer selectivity. Basically, how does this enzyme discriminate between an L amino acid and D amino acid? Because the challenge that this enzyme faces in the cellular pool is that you have abundant L amino acid tRNAs and very few D amino acid tRNAs. And if it starts cross-reacting with L, then it's not a good and healthy scenario for the cell. So we wanted to understand how does this enzyme discriminate between these two forms of amino acids. So we went ahead and started crystallizing this protein complex with a ligand analog, and after a lot of effort, we could actually get these crystals which diffracted well, and we could solve the structure of this enzyme. So don't bother about these statistics, it's just to show that the conditions in which we got crystals and the refinement that we did. So when we solved the structure, what we found, this is a D-tyrosine analog, which mimics the actual substrate. So there was a technical limitation why we couldn't use the actual substrate for crystallization, because these substrates are very labile. They break off because of this ester bond. It breaks off spontaneously. So we had to use a substrate analog, which has an amide linkage, which makes it not hydrolyzable. So when we solved the crystal structure of this enzyme with this analog, we found that the side chain of this D-tyrosine actually protrudes from the pocket, so that there is no recognition of the side chain of this amino acid. And this clearly showed why just one enzyme can hydrolyze multiple D-amino acid substrates. So this gave the basis for just one enzyme doing multiple functions in that context. What we also found that there is an important glycine cis-proline motif at the dimeric interface, which is involved in capturing the chirality of this substrate. However, even after we solved this crystal structure, we were not sure what exactly the mechanism of this enzyme was, whether it was D-chiral selection or L-chiral rejection. So what we did to answer this, we again went back to crystallization and solved the structure of this enzyme, this time in complex with glycine substrate. And as you know, glycine is the only achiral amino acid of the 20 genetically encoded amino acids. And in the crystal structure, we saw that even glycine can be accommodated in the same active site pocket of this enzyme. Interestingly, when we analyzed it closely, what we found there's no, the amino group of glycine is actually in a flipped orientation compared to the amino group of D-tyrosine. So this kind of showed that there's no specific selection for the D amino acid. But it also indicated, since this active site can accommodate even achiral glycine, it can as well act on achiral glycine, which was never anticipated by the scientific community before. So we went ahead and did biochemistry, and what we found that this enzyme very actively cleaves off glycine substrate, but it does not act on L substrate, even the minimal L substrate, the smallest L amino acid, which is L-alanine. So this was these observations clearly told us that the basis on which this enzyme works is strict L-chiral rejection and not D-chiral selection, so that it can act on both D and glycine, but not L. But this leads us to a paradoxical situation in the cellular context, because if this enzyme is acting on glycine, then how does protein synthesis work? Because to have proteins, you need glycine. So this creates a paradoxical situation. So how is this paradox, overcome in the cell? So what we thought that there's this factor, elongation factor TU, which is responsible for delivering the amino acid tRNAs to the ribosome for protein synthesis. So we speculated that probably EF2 might be responsible or involved in protecting this species from TTP. So we did again biochemistry, and what we actually found when we incubated this substrate with the enzyme and EF2, it actually protected the substrate. Whereas if you see when there's no EF2, this cleaves off substrate. So EF2 indeed provided some protection to the substrate, the glycine substrate. However, this protection was not very strong, and when we increased DTD's concentration level just fourfold, so the entire protection was gone. So this clearly indicated that in the cell, if you try to overexpress this enzyme, this can actually lead to toxicity. So we went ahead and tested this hypothesis, and we did spot dilution assays with our E. coli cultures. And when we overexpress this DDD, you can clearly see Eventz toxicity that happens. So this is the uninduced culture, and this is induced with IPTG. So there's remarkable toxicity that happens when we overexpress this enzyme, and which could be rescued by supplementation of glycine, but not by alanine. So which clearly indicated that when we overexpress this enzyme, it can actually lead to cellular toxicity. Another aspect of this enzyme that we wanted to understand was its mechanism of catalysis. How does catalytic function happen? So, if you look at the active site, these are the three residues which could be responsible for catalysis. But when we mutated each of these residues individually, the catalysis was still intact. So, which is surprising because enzyme catalysis are based on side chain chemistry of proteins, right? But in our case, we found that side chains are actually dispensable; they are not involved in catalysis. So, if side chains of proteins of enzyme are not responsible, then what else? So, the only thing that is possibly involved here is the 2' hydroxyl group of the tRNA itself. So what we did, we modified our tRNA, and instead of hydroxyl group, we replaced it with hydrogen, making it dehydroxy, or a fluorine, and we used this modified substrate to test our hypothesis. And what we found that DDD is totally inactive on these 2' modified substrates, whereas it is very active on 1' substrate. There's no activity whatsoever of this enzyme on these modified substrates, even at 10,000-fold excess enzyme concentration in the assay. So it basically clearly told that 2' OH is essential for catalysis by this enzyme, which means DDD is basically an RNA-based catalyst like the ribosome or responsosome or other ribozymes. So we came up with this model for a glycine-based editing paradox. So DDD does not act on L-amino acid tRNAs, but it is very efficient in removing this D-amino acid discharge on tRNA. In case of glycine, it does misediting if there is no EF2, but EF2 under normal cellular concentrations is able to protect this achiral substrate. But if we overexpress DDD, then it can actually lead to toxicity. But before I end, I'd quickly like to tell you, so we were wondering, like, what is, if DDD's activity on glycine is not required, then why is it intact? Why has it remained during the course of evolution? What is the significance of DDD's activity on glycine? Is there something more than to it that needs to be out? So what we know is that this enzyme, alanine tRNA synthetase, is responsible for charging L-alanine on tRNA alanine, but it also makes the mistake of mischarging L-serine and glycine on tRNA alanine. So we thought that probably DDD might be involved in removing glycine, which is mischarged on tRNA alanine. And again, we tested that, and we found that DDD indeed does a very efficient role in removing glycine from tRNA alanine. And if in a DDD knockout background, if we supplement glycine, it actually causes toxicity. And this function was totally unanticipated about DDD playing an editing role of removing glycine from tRNA alanine. So this is the final model that I would like to show here. So it was known that DDD is involved in removing D amino acids. What we found out is that DDD can actually act on glycine, which is the achiral amino acid, but normally it is protected by EF2, whereas in case of glycine, which is mischarged on tRNA alanine, DDD can do this editing function even in the presence of EF2. So with this, I'd like to thank you all for your time and patience, and I'd be happy to take any questions. Thank you.